Hi everyone, sorry I can't be there with you today, but hopefully this video will make things go a little more smoothly for you. The main focus of today's convergence tests will be on these that are here. So direct comparison and limit comparison, which are pretty much the same as what we did when we covered them in chapter 6 and 8. And then we're going to also continue to use then the geometric series, telescoping series, the nth term test, and the p-series test. So I only have 6 practice problems for you today. And then after I go over these in the video, then you're going to do a Google form. You can either work on that to, like with somebody either on Zoom or in class, or you can work on it independently. But you do want to get that done before class is over. All right, so here are the first two. The directions say determine if a series converges or diverges, and then make sure you state the test and show work. Showing work is kind of a big deal. That's an AP thing, right? So you have to make sure that you're showing your work. So my inclination tends to be to try and use direct comparison or limit comparison to begin with. I'm going to try direct comparison here. And when we did this before, we did pretty much the same thing we're doing now. So I'm going to just start off by saying, well, 5 to the n plus 5 is going to be greater than, and I want to pick something thinking in the future of what will work. So I'm going to pick it's greater than 5 to the n, because then when I take the reciprocal, I get that this thing on the left, 1 over 5 to the n plus n, will be less than 1 over 5 to the n. And then you have to know what that means about this. So usually what's a good idea is before you really start, you should probably think ahead and go, well, I know that the sum from 1 to infinity of 1 over 5, and if it helps, write it like this, 1 over 5, the whole thing to the n, is a geometric series that converges. So since it's a geometric series that converges, and the thing I'm comparing it to is smaller than what I know that converges. So if this thing converges and then there's a new thing that's smaller, that means by the direct comparison test. So I want to make sure I say that by direct comparison test, the sum or the series from 1 to infinity of 1 over 5 to the n plus n converges. Direct comparison test tends to work really well when you're adding things in the denominator, assuming that you can separate it apart and have something that converges. Okay, so I say that because the one that on the right-hand side is subtracting, and you cannot use direct comparison test for that, because if you just think about what's happening over here, you would say 4 to the n minus 4 is less than 4 to the n, and then you'd reciprocate and it wouldn't work. But you do still want to use that 1 over 4 to the n geometric series, because that does converge. So I still want to use that, and I'm still kind of confident that this thing is going to converge. It's not getting that much smaller. So if I can't use direct, then it's probably a limit comparison problem. So we're going to do the limit as n goes to infinity, and I'm going to compare it, the thing I have, with this 1 over 4 to the n. So we're going to compare it like this. This becomes the limit as n goes to infinity of 4 to the n minus n over 4 to the n. And these two exponentials are behaving in the same way. They have their same n behavior, which means that the limit would be their coefficients. This n doesn't matter to us in this problem. So the limit is equal to 1. And when the limit is between 0 and infinity, as long as it's a number, that means that the two series do the same thing. So we're going to say by the limit comparison test, this new series that we have, 1 over 4 to the n minus n, converges. And again, that's because the one we compared it to also converged. If we had compared it to this thing here and you got this answer of 1 and this original thing diverged, then our new series would also diverge. All right, next two, I guess. So when I look at these, I want to think about what I know, like just simplifying it out. So when I look at this, I see I have n to the third in the numerator and I have n to the fourth in the denominator, which if you kind of think of canceling those, that's really behaving like 1 over n. And we know that 1 over n diverges. The p-series tells us that that thing diverges. So if I can compare it to something in some way, compare my new one to 1 over n, then I should be able to get a divergent thing. This is not a good choice for direct comparison. That's really not going to work. This is going to need to be a limit comparison problem. So the limit as n goes to infinity, I'm going to compare it to 1 over n. I'll switch it up. Oops. So first problem, I did the new thing in the numerator. Don't know why it switched colors. Now we'll put the new thing in the denominator. Okay, so it gets here. When I flip it and multiply it, I get 3n to the fourth over 2n to the fourth plus 7. And that limit is 1. And again, the limit being 1 doesn't tell you that your thing converges. It tells you that they behave in the same way. So the original one, the new one we compared it to diverged, therefore the new one diverges. So we say by the limit comparison test, the series from 1 to infinity of 3n to the third over 2n to the fourth plus 7 diverges. Okay. Number 4. Number 4 is a test that I think we tend to forget about, or it's kind of the last thought, but really it should be something you should be thinking of in your head from the very beginning. So when you look at this, okay, you're adding something to 1. You're adding a small number, and it's continually getting smaller, but you're still adding something onto 1, and you are squaring it. So when you go to just take the limit of this whole entire thing. So the original problem here, if I take its limit, I'm getting something that is equal to 1. Okay, so again, these things are getting smaller, so this thing is going to infinity if you want to separate it out, right? Sorry, going to 0, excuse me. So this, when n goes to infinity, this part of the limit goes to 0. So therefore, the whole limit goes to 1. And we know by the nth term test, if the limit of the thing here, of the sum formula in here, does not go to 0, then this thing diverges. So you would just say by the nth term test, as n goes from 1 to infinity of that thing, this whole series diverges. Remember, the nth term test only tells you divergence, it can't tell you convergence. So if this had been 0, then it wouldn't have necessarily meant it converged. It just meant you don't have enough information to use this test. All right, last two. Number 5 can sometimes be a little confusing for students, so you want to think about what you're going to compare it to. It's probably a good limit comparison test problem because of that subtraction stuff going on. The subtraction makes the direct comparison a little tricky. And I'm just going to think about the highest power here. So I'm going to think about the square root of n to the 8th. That's kind of like n to the 4th in the denominator, and then there's an n in the numerator. So n over n to the 4th, it's kind of behaving, or I'm anticipating it's going to behave like 1 over n to the 3rd. Okay, that's my guess. So I'm going to compare it to that. So I'm going to do a limit comparison and say the limit as n goes to infinity. It doesn't matter what you put in the numerator, if you put the new thing or the old thing. Oops. Oops, that looks funny. Okay, so flip the fraction here. You do need to show all of this work, ladies and gentlemen. You cannot skip. I mean, you can skip some of the limit simplification steps, but you can't skip writing it out. So when I flip this up, this thing here is getting multiplied to n to the 3rd. So it's going to be n to the 4th minus 4n to the 3rd. or however you want to keep it factored, that doesn't matter. The main thing is for you to realize that this gives a limit of 1. And so since this limit is 1 by the limit comparison test, the original series converges. And that's because we knew that the 1 over n to the third converged as well. All right, last one. Notice, by the way, every single time I'm doing this comparison, I'm using a series that I know, but you have to know those. So you have to know that this thing here, this is a p-series problem, right? So this is a p-series that converges because the p is greater than 1. Okay, so although we aren't doing an exact p-series practice problem, you're still using the p-series in the problem, or maybe you're using a geometric series as well. So you're not just seeing p-series on their own. All right, this one, I like to use the fact that sine is less than or equal to 1. We know it's greater than or equal to -1, but I don't need to worry about that part. I just need the less than or equal to 1. And I'm going to divide the whole entire thing by n squared. So I now have this thing that I know. Okay, so this is another p-series problem. I know that this converges. And my sine expression is less than something that converges. So that means my new thing converges by the direct comparison test. As you start to do these things, it's really important that you think about what you're comparing it to and what the thing that you compare it to does. Okay, so if you don't know what you're comparing it to, what its convergence or divergence is, this isn't going to be helpful at all. All right, hope that helps. Don't forget, you can always pause the video, you can come back to the video, do whatever you need to make sure that you understand, and then be prepared to ask questions if necessary when I see you in class.